Zeros of polynomials. Okay, before we jump into the notes on this, we are going to first consider this. If I have the number 15, okay, I can rewrite it as 3 times 5. Now, I know that there are other factors of 15, but here are two factors. So any two numbers that multiply to make another number, right? In this case, 15, they are factors. Okay, I know 1 and 15 are also factors, right? So we know what factors are when it comes to numerical values. With polynomials, the same thing applies. So if I have a polynomial, we'll call it p of x, and I say that it's equal to the quantity, I don't know, let's go x plus 2, x minus 3, no remainder. Then if those two quantities multiply together and make a polynomial, then they are factors of that polynomial, okay? Now, what do factors tell us? Well, if there's no remainder now, we have these factors. I know then by looking at this, if x was a -2, that factor would equal 0, right? So basically what I'm getting at is if we set the factors equal to 0 and we solve it, and if we do that for both of them, we get the zeros of the polynomial. Why? Because when these two numbers are put into the polynomial function here, the answer will be 0, which alludes to if -2 is inserted into the function, 0 comes out. If 3 goes in, 0 comes out. So if you look at it this way as ins and outs, then we can see that the zeros are indicating the x-intercepts. Okay, well, that was not supposed to happen. Intercepts. Now, another way that some books talk about zeros and x-intercepts is they call them roots. So if you see the word roots, just know that that is the same thing. So factors of the polynomials, they tell us nice things about the polynomial. They tell us the zeros and they tell us the x-intercepts. Okay? Now, the factor theorem, that's kind of what we just looked at. If we have this x minus c and it's a factor, then f of c will be 0. It's also notable that if it is a factor, then there is no remainder. Think about our previous lesson and how we were doing polynomial division. If it divides it nicely, the quantity, then there's no remainder, and thus is a factor. Okay, so that's what that is. Now, this lends itself well to the remainder theorem. So consider this. If we take a polynomial and we divide it by a quantity, in this case, they're saying x minus c, okay? If there's no remainder, it's a factor. If there is a remainder, then that's what f of c will equal. And you're going to see that right here in this first example. So we are going to use this remainder theorem to evaluate f of 2. Okay, so that's what we're looking into. What is f of 2? Well, I'm basically testing the factor x minus 2. And 2 would go in the box because that's the 0 that we're hoping for. Okay, it's not going to end up being a 0, but you will see that we get a remainder, and that is what the function is equal to when 2 is inserted into it. I'm going to do synthetic division. It is the easiest and the quickest, in my opinion, especially without a calculator to help us. And I mean, you could do longhand polynomial division, but synthetic is pretty slick here. So 6, -1, -15, +2, -7. Okay, so now bring the 6 straight down, multiply by the number in the box, add them, multiply by the number in the box, add them, multiply by the number in the box, add them, multiply by the number in the box, add them. Did not get a remainder of 0. Instead, I have a remainder of 25. Here's what this means, and I know we discussed it in the previous section, but here's what this means. This polynomial, f of x, we tried to factor x minus 2 out of it. What we got for a quotient was 6x cubed. Remember, it was quartic, so if you take a linear piece out of it, you're down to a cubic and so on. 6x cubed plus 11x squared plus 7x plus 16 plus the remainder of 25. Notice the remainder is tacked on the end. So this is what we tried to take out. This is what we were left. And then we always have to add the remainder on. Okay, so if you think about this, if I tried to plug 2 into the polynomial, this part would be a 0. This part, it doesn't matter what it is because you're going to multiply it by a 0. And then ultimately, you'll add 25 after that. So f of 2 is 25, the remainder, which is what the remainder theorem is telling us. Now, one more notable here is you absolutely could have taken your function and plugged 2 into it. So it would be 6 times, let's see, 2, 4, 8, 16, minus 8, minus 15 times 4, plus 4 minus 7, 60, 70, 80, 96, minus 8, minus 60, plus 4, minus 7. You could certainly do all of this math and get the same answer. But I know it's going to be equal to the remainder, so that's good enough for me. Okay? All right. Now let's look at this next example. It is telling us x plus 2 is a factor. It wants me to find all of the remaining factors. Okay, and then use the factors to find the zeros. So if x plus 2 is a factor, then negative 2 is the 0. Set that equal to 0 and solve it. Okay, so this is my 0 of the polynomial. My coefficients are 1, negative 6, negative 1, positive 30. Bring 1 straight down, multiply by the number in the box, add, multiply by the number in the box, add straight down, multiply by the number in the box, remainder is 0. We like that the remainder is 0 because this means that our function, they don't call it f of x there, but I think I'm going to here. The function, we were able to take x plus 2 out of it. The quotient it was cubic originally, so now we're at x squared minus 8x plus 15. Okay, so I did show that it was a factor. So first part done. Second part is find all remaining factors. So I'm looking at the quadratic piece, and I see it as factorable. If you don't know how to factor or don't see it as quickly factorable, you can always do the quadratic formula, solve for the zeros, and work it backwards, okay? But I see that an x minus 3 and an x minus 5 will be the factors. So now, here are all of the factors. So that part has been done. Now it says use the factors to find the zeros. So I'm going to set each factor equal to 0. This one I already know. And solve each one of them. And there are our zeros for this polynomial. All right. I'm going to call that part 1.